Okay, in this discussion, we're going to talk about if and only if proofs, which you know are called biconditional statements, proving biconditional statements, or proving equivalent statements. Okay, however you want to word it, that's what we're going to cover. Okay, now suppose that you had a proposition that was a biconditional. Suppose it said P if and only if Q. Remember, an abbreviation is IFF if you want to use that. Okay, the key is to remember what that means. That means P implies Q and Q implies P. So that means that you're wanting to prove actually two statements. Okay? So you need to prove this. I meant for that to be red. You need to prove that, which is one statement in itself. Okay? And we talked about how to prove conditional statements. And then you also prove that. So there's two proofs. Well, let's call them subproofs. There's two subproofs, and you put them together and they give you one proof of that. Okay? So let's write this proof. So we'll put prove P implies Q. And I'm not going to write here how to do that because we covered several ways. You could do it directly, which would be suppose P derive Q, or you could do it by contraposition, which would be suppose the negation of Q derive the negation of P, or you could do it by contradiction, which would be suppose the negation of P and derive a contradiction. So there's three ways. We talked about those in the previous lecture or lectures. Okay? But however you choose to do it, you prove P implies Q. And then you prove that Q implies P using direct contraposition or contradiction. And then that gives you your proof of P if and only if Q. Okay, so let's practice. Let's prove this proposition. The integer n is odd if and only if n squared is odd. I'm going to write IFF as an abbreviation. Okay, now just so that you understand, the fact of n being an integer applies to this and also applies to this. Okay, so I would probably, for myself, I would probably label them like this. I'd probably say P, this is P. N is an odd integer, would be P, and Q would be this. N squared is odd and n is an integer. Do you see what I'm saying? The part about n being an integer applies to both directions. Does that make sense? So I'm going to label n is odd as P and n squared is odd as Q. But for both of those, part of it is n being an integer. Okay? So first, let's do what people usually call the forward direction. Okay? I'll label this here. P implies Q. Or, to be honest with you, a whole lot of people will just write this. Okay? All right. So let's do that proof. So we will say, let n be an integer, and suppose n is odd. So I want to try to prove what? I want to try to prove that n squared is odd. That's my goal. Okay, so let's just fill in the steps. All right, I don't have much to go off of other than the definition of odd. So if n is odd, then what does n look like? It equals 2 times an integer plus 1. Okay. So what would n squared look like? Well, it would be 2k plus 1 squared, which looks like this. 4k squared plus 4k plus 1. I'm trying to show that n squared is odd, so I need to show that n equals 2 times an integer plus 1. Here's the plus 1, so probably this needs to be my 2 times an integer. Can I make that look like 2 times an integer? Sure, just factor out 2, right? Okay, let's do that. I would get 2 times 2k squared minus 2k, okay, and then my plus 1. Does that mean that n squared is odd? Yes, because what's really important? That's an integer right there, and I need to point that out. Okay, so I can do it like this. I can say hence n squared is odd since 2k squared minus 2k is an integer. Okay, and that takes care of proving one direction. That proves P implies Q. Okay, now I'll do the other direction, and people oftentimes put this here. Okay, it's not mandatory, but people oftentimes do that, especially people who are still learning. Okay, just helps them keep straight what they're trying to do. Okay, so I would say let, what should I say? I don't want to just say let n squared be odd, because this is important. This is a complete proof by itself. It's not a proof of P if and only if Q, but that, what I circled in red, that is a complete proof of P implies Q. It's a sub-proof within our larger proof. It has ended. So what I said here, let n be an integer, that is not automatically going to carry over to here, because that was part of a sub-proof that has now ended. Okay, does that make sense? So I'm just trying to say that I should start over and say let n be an integer, and suppose n squared is odd. Now there are ways around it. There are other ways to write this where I would not have to repeat let n be an integer. I'll show those to you in a minute, but let's just continue along with where we are here. Okay, so let n be an integer and suppose n squared is odd. Okay, then what? Well, let's think about it. And let's see if this gets us anywhere. Then n squared would equal 2 times an integer. And again, you can use k if you want, because I used k before in a sub-proof, but that has ended. K has been released back into the wild. You can use K again if you want. If you don't want to, then choose a different letter. There's lots of letters, so if you want to be on the safe side, you can choose something else like L. Okay, now I'm going to run into a problem here. What I've written is 100% correct. However, I'm not sure how I'm going to use that. N squared equals 2L plus 1. So what does N look like? I'm not sure, am I? I mean, it would be the square root of 2L plus 1, but how am I going to use that? I can't break that down is what I'm trying to say. So I'm kind of hit a brick wall here. So what do? I don't keep ramming my car into the brick wall. I see if there's a way around it. But if I don't find a way around it fairly quickly, then what do? I say, maybe I should be going a different direction altogether. Okay, so maybe, I mean, I started off trying to prove this directly. Maybe that's not the direction to go. What are some other options? What about if I try contrapositive? In other words, what does that mean? What if I suppose the negation of Q and derive the negation of P? No, I'm sorry, I said that backwards. This is a good example of how you can mess things up. So let's be very careful here. I did that on purpose. I said it backwards just so I could fix my error. No, not really, but let's be very careful. Up here we proved P implies Q. Okay, down here we're trying to prove Q implies P. And if I choose to use, why did I write that there? It should be up here. And if I choose to use contraposition, then that means what? It means assume the negation of P and try to derive the negation of Q. Okay, I started out by assuming Q, trying to derive P. I ran into a brick wall. So I'm going to try a different direction, a different tactic. I'm going to try doing this proof by contraposition. I'm trying to prove Q implies P, so I'm going to suppose the negation of P and try to derive the negation of Q. Okay, so let's try it that way. Let n be an integer and suppose n is not odd. Some people feel like you should say n is not odd, and then say, therefore, n is even. That's totally fine. I think that's going a step beyond. I think that we all are totally clear on the fact that an integer that is not odd is even. So I'm totally fine with people saying, suppose n is even. That's the same thing as saying n is not odd. I don't think that they have to be stated separately. Okay, that's my feeling on it. And I'm not being lazy. I mean, I'm actually a stickler on being precise. But again, there's a fine line between being precise and going overboard. Okay? And that's something that you just have to develop a feel for. All right, so let n be an integer and suppose n is even. Okay, I think that's going to be much more helpful. Then n equals 2 times some integer. So n squared would be that squared, right? Which is 4l squared which is even, isn't it? Because that equals 2 times the integer 2l squared. So hence n squared is even, since 2l squared is an integer. So thus, if n squared it is odd, then n is odd. And it's not a bad idea to point out, in case somebody gets confused right there, how you made that jump. How did I do that? I did that by contraposition. So if somebody did get stuck, they should now be able to say, oh, I see, yes, because they showed that this implies this, and so therefore the negation of this would imply the negation of that. Okay? So there we go. I proved one direction. I proved the other direction. And so now together, I put them together, okay? And I say, therefore, if n is an integer, then n is odd if and only if n squared is odd. And that's the end. Okay? Now, a couple of formatting issues. Actually, maybe I should leave that green highlighted. Okay, a couple of formatting issues. This is not mandatory, but I think it's a really, really good idea. Notice something that I did in spacing. So look, here's a subproof proving that. Here's a subproof proving this, which we did by contraposition. Okay? Together, they make one long proof. And it is not really long, but it's starting to get there, right? How many lines is that all together? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. Okay. I don't consider 10 lines long, but I do consider it as sort of the boundary. Once you get over 10, you're starting to get, you know, maybe a little bit long. Okay. The point I'm trying to make is this. If I were to just scrunch that all together, it might be a little bit hard for someone to follow. They should be able to follow it though, and that's always your question. Would a reasonable person be able to follow this? Okay. They should be able to follow it even if it's all scrunched together. However, it's no skin off my back to do the reader a little bit of a favor and put, notice what I did here. I put a little bit of a space. Oh, here's where the proof starts, right there. Okay, I put a little bit of a space here and a little bit of a space here, just to make it a little bit easier to tell what the formatting is. This is a subproof, and then it ended. You could even go as far, if you want, as putting that symbol if you want to. I don't normally see people do that, but you could. But I think putting a double space there is good enough, you see. And it breaks things up, so the reader should be able to see, oh, there's things broken up. So this part right here is one thing, and then apparently this here is a different thing. And so it helps them keep things straight, the two different directions. And then the extra space down here shows that this is a third thing. And what is the third thing? The third thing is just combining the first two things. You see what I'm saying? I think that's a good idea. I encourage you to do that when you're doing if and only if proofs, to put in that spacing like that. Okay, another thing. Is this stuff over here necessary? No, but an awful lot of people do it. It's a good idea. But let me say a few things about that. So that third one there, showing the contraposition, that was just so you could follow what we're doing, and because I originally said it backwards on accident, so it was partially to help me straighten things out. That would normally not be there. It would normally be something like this. And like I told you earlier, a lot of times people don't even put the P and Q. What they would normally do is this. This is very, very common to see students do. Very common. And it's not a bad idea. I actually think you should probably do that while you're learning how to do these, so that you can keep things straight for yourself as well. Okay? But a professional mathematician in a math journal would not put things like this over here on the side. Okay? You would not see those. And in that case, then I think that there needs to be some wording here showing that you're switching directions. So I would say, I would do it like this. I would say, on the other hand, let n be an integer and suppose n is even. Or something as simple as the word now. Now let n be an integer and suppose n is even. Just something to indicate, okay, look, now we're doing something new. We're doing something different. This is not just a continuation that follows from the previous line. We are starting over again on some new subpart. Okay? So it's kind of like the word now is kind of like playing the role that this little indication over there would have been playing. It doesn't, you know, say the word now doesn't actually say a direction, but it says, hey, we're switching from what we were doing before. We're switching directions. Okay, another thing I want to throw out there, I was talking earlier about repeating let n be an integer. What if you felt like, it's stupid to say that again down here and I don't want to? Okay, here's something we could have done. I could have separated that out and did this. Let n be an integer, not as part of the first subproof. Take it out. As a standalone statement. And then you wouldn't need it there. But I would put the word now or the phrase on the other hand. Does that make sense? So now this really has four parts now. One single statement there, and then this part which is proving one direction, and then this part which is proving the opposite direction, and then putting those together. Putting together these three things. Okay? But the bottom line is simple. The bottom line is simple. The details might not be simple, but the overall thing is simple, and that is an if and only if statement is two conditionals Same two parts, but both directions. And so you prove one conditional in one direction, you prove the conditional in the opposite direction, put them together, you have proven the biconditional. Okay? And also another way of saying that, don't forget this, that if and only if can also be expressed using the phrase is equivalent to. This could have been written, if n is an integer, then n is odd is equivalent to n squared is odd. I could have worded it that way. You don't normally see the phrase is equivalent to used when there's only two statements, but you often see it when there's multiple statements. So here's a really good example. It's a long proof from linear algebra. Okay? So it says, suppose A is an n by n matrix. Then the following statements are equivalent. Okay, and now I'm going to write all of them all at once so that it doesn't spend a lot of your time while I'm writing. Okay, so we have 6 statements there. And the theorem says that these 6 statements are equivalent. Okay, A is invertible. The equation AX equals B has a unique solution for each B. The equation AX equals 0 has only the trivial solution. The reduced row echelon form of A is the identity matrix. The determinant of A is not 0. 0 is not an eigenvalue of A. Okay, I don't want you to worry at all or even spend any time thinking about those 6 statements and what they say. We're not going to prove that. We're not going to try to figure out why they are equivalent. I just want to talk about what does it mean to say that 6 statements are equivalent, and to prove that, what do you need to prove? So what is the theorem saying, and what do you need to prove? Okay, so believe it or not, that one theorem contains, let me count them and see. If my counting is correctly, it contains 15 biconditionals. Okay? So this is what it is saying. Let's see if I can label all 15. Okay? So it's saying that statement A is equivalent to statement B, and statement B is equivalent to statement C. Here, let's actually write that on a separate line. And it says that C is equivalent to D. You can tell where I'm going with this probably, right? D is equivalent to E. E is equivalent to F. So those are, I think, more or less straightforward. 5 biconditionals. But it's saying more. It's saying all of the statements are equivalent to each other. So A is equivalent to the other 5. A is also equivalent to C. And it's also equivalent to D. And it's also equivalent to E. And it's also equivalent to F. And B is equivalent to all other 5. I already have that it's equivalent to A. But it's equivalent to C as well. I already have that. So I've got two of them of what is B equivalent to. But B is also equivalent to D. That's not written down, but it's still true. And B is equivalent to E. And B is equivalent to F. What is C equivalent to? It's equivalent to A. I already have that written. And it's equivalent to B. I have that written. And it's equivalent to D. I have that written. But it's also equivalent to E. And it's equivalent to F. You see where I'm going with this? There's a lot of biconditional statements stated in this one theorem. That's what I'm trying to get at. So far it is written how many there? 1, 2, 3, 4, 5. There's 14 already. I think I said there would be 15. Was I right? Let's see. What about D? I have A and D. I have B and D. I have C and D. I have E and D. But what about F and D? I think that's all of them. Let's just check. How about E? There's A and E, B and E, C and E, D and E, F and E. Okay, got all of those. And let's check for F. There's A and F, B and F, C and F, D and F, and E and F. So I got all of those. Okay, so there we go. I was right. There's 15 statements being stated here. Each one's a biconditional. So in theory, you would have 30 subproofs, right? But do you have to do all 30? I think obviously not, because, for instance, here's just one thing to point out that's obvious. If you prove A is equivalent to B and B is equivalent to C, then haven't you already proven that A is equivalent to C? Yeah, by transitivity. So that's one example of where you don't have to prove all 15 of these statements. Okay? So what's the minimum? The minimum, so I said 15 earlier, and they're biconditionals, so that would actually be 30 subproofs. The minimum that you could get away with is 6 subproofs. That's not necessarily the easiest way, okay? The shortest way would not necessarily be the easiest. But the idea is this. You need to form a chain of conditionals that would allow you to get from any one statement to any one statement, including back to itself. So the easiest way to go, no, sorry, not easiest, but the least number of hops would be that you could do A implies B, not even biconditional there. I meant to write only one direction, okay? You could show A implies B, and B implies C, and C implies D, and D implies E, and E implies F. That's 5 steps. I say steps because I'm imagining like these are rocks on a stream that you're trying to cross. You see this one? That's why I say steps. Even that, though, is not enough. I can get from A to anything else, but I can't get, based upon what I've shown right there, I can't get from B to everything else. For instance, I can't get from B to A. You see what I'm saying? But if I put one more step, F implies A, you see now I have the ability to get from any one statement to any one statement, because there's a loop that I have formed, you see. Okay. So that means that every statement implies every other statement. Okay? And that's really what a biconditional is. In the extreme small case, you would just have two statements, A and B. To say A if and only if B means that each statement implies the other statement. Here we have every statement implies every other statement. So that string, if I could accomplish that, 6 subproofs, 6 conditionals, if I could accomplish that string, then I would be proving these 15 biconditionals. Okay, now I said that's the shortest number of steps. It's not necessarily the easiest. It might be easier to do something like this. Let me pick a different color. It might be easier to do something like A implies B, and maybe it's really easy to get from B back to A. So I could do that. And then maybe B implies C, and C implies D, and D implies E, and E implies F. And then I would not have to show that F implies A. If I could just show that F implies B, then I would be fine. Can you follow those arrows and see that you could get from any letter to any other letter? Okay, so there's lots and lots of possibilities. You could do, let's pick a different color here. You could do something like maybe A implies B, which implies C, and maybe C implies F. Let's do it like this. Whoops. And maybe F implies A. And F also implies, oops, I forgot to put an arrowhead on there. There we go. Let me make that big arrow neater. Okay, well, that's not much neater. Okay. And maybe F, or maybe C also implies E as well. And what else is missing? There's no D yet, right? And maybe E also implies D, and maybe D implies F. Could I get from any statement to any statement if I proved those 7 conditionals? I think so, right? So the bottom line is, when you have a string of statements, multiple statements, even as few as 2, but like I said, 2 statements, then that's just a simple biconditional. But if you have more than 2, and it says these statements are equivalent, then the idea is not any different. It's just that there's more stones across the stream. Okay. The smallest case, when there's 2 statements and it's just a simple biconditional, then that's just the 2 banks of the stream, and you just have to be able to step across the stream in one direction and show that you can step back in the other direction. Okay, but the more complicated case is when there's more than 2, then that means there's some stones also, and you just have to show that there is a path that you can follow that will take you through all the statements. Okay? Including, you need to be able to get back where you started. That's how you prove that multiple statements are equivalent to each other. I think what would be the easiest mistake to make would be to, I guess somebody could show that A implies B and B implies C and so on, and say, there we go, we got them all, and not realizing that doesn't show you that E implies A. It only shows you that A implies E. So I think that's maybe the easiest mistake, is to not realize that you have to show that you can get back here somehow. Maybe in one step like that, by showing that F implies A, but maybe that's too hard. Maybe you can show that F implies C and C implies A. Or F implies C and C implies B and B implies A. You know, something. But the point is, the chain has to be bidirectional, which doesn't necessarily mean that each direction you have to prove in both directions. It just means that you have to be proving such that your arrows can get you back to any place behind you. Does that make sense? If not, you can ask me about it during the discussion. I think you probably got the idea, though. All right, there's not going to be any more lectures for about 9 more days, because we have Thanksgiving break. So this will be the last lecture for a week. I'll give you some stuff to work on for practice. And other than that, we'll see each other again in about 9 days.